Hey folks, here's another electrostatic question. It says two identical small metal coated spheres R and S are given identical charges each. Like looking here, you have R and S, charge R and S, they have identical, right? So they are suspended at the same point from the ceiling by means of identical light inextensible insulated thread of equal length. Guys, if you look at these charges, they're identical. If they're positive, it's going to be positive. It's positive 40 nano coulomb, 40 nanocoulomb, and then the length of the threads here from the ceiling, they are equal, so they have equal length there. Now it says the threads of negligible mass, we neglect the mass of that when the system is in equilibrium. When I say the system is in equilibrium, that means this is stationary, it's not moving. The angle between the thread is equal to 60 degrees, while the distance between R and S is 5 centimeter. So guys, if you look at this, they forming the angle between them, the thread, it's 60. So it simply means that to me, guys, it forms an isosceles triangle there. That means that if this is 5 and also those sides are 5 and 5, right? And the angles there, if this angle is 60, this one is 60 and this one is 60. An isosceles triangle, no, it's not an isosceles triangle, it's an equilateral. It's an equilateral triangle, right? All sides are equal and all angles are equal. The isosceles triangle is the angle where the two sides are equal, right? Right. Now that's not the point. Now guys, it says state Coulomb's law. We know Coulomb's law. And then now it says draw a label free body diagram showing all the forces acting on sphere R. So our interest is here. So drawing a free body diagram there in 7.2, I'll draw it here. So here's the sphere R. Represent the sphere by a dot, and the forces that are acting on sphere R, it's tension there that is going in that direction. So it's going to be T for tension there, and you have the gravitational force that is going downwards there. And these, if are identical, these two charges, this one is repelling this one in that direction. So there's an electrostatic force that is experienced by don't know what's happening there. There's an electrostatic force there. I'll put it as E. As E is an electrostatic force that is due to S, right? Those are the forces that are there. Now it says calculate the mass of sphere R. So we want the mass of this. Now looking at these forces, and this is at equilibrium, it's not moving, right? If it's not moving, guys, if I can turn this vector diagram, this free body diagram, into a vector diagram, so I'll have the tension like that and the gravitational force downwards and the electrostatic force that way, right? And if you're looking at that, guys, looking here, there's a tension force here and there's an electrostatic force in that direction, and there's a gravitational force. So this force, guys, it's going to be 60, this one, and you have 90. Why is that the case? Why is that so? So guys, if you, the angle here, which is, it's this angle, right? It's this going to be this angle here, as I've mentioned, it's 60, and that means it's going to be this angle there. There's a tension there, and there's a frictional force there that is going in that direction, the electrostatic force that is going in that direction, and you have a gravitational force there. So it's going to be 60 there, guys, right? So now to calculate this, guys, now the first thing that you have to do, since you have now you here, you're not given the tension here, you're not given the tension, and they want the gravitational, the mass here. We're looking for the mass. That means you have to get the gravitational force. But before you get the gravitational force, you must get the electrostatic force. The electrostatic force, it's easy to get it because you have both charges and the distance between them. So what are we going to do? I'm going to calculate that electrostatic force. So it's Ks and what? And R over R squared. It's going to be 9 times 10 to the power 9, and the S, it's 40. They're both 40, 9 no coulomb, 9 no, and it's times 2, and then the distance between them, it's 5 centimeter, and then we divide by 100 square. I hope that makes sense, guys. And then when you punch that in the calculator, the answer there, it's going to be 5.76 times 10 to the power negative 3 newtons. So this is the electrostatic force between these two, right? Now, getting that electrostatic force, that means now I have this force, but now I have to get the gravitational force in order to get that mass. So what I'm going to do, I'm going to use the trig ratio, which is opposite over adjacent. I wanted the gravitational force, and I have the adjacent, which is the electrostatic force, which is, what is that? It's tau, which is the tan theta. So it's going to be tan theta, which is opposite over adjacent. So my tan, it's going to be tan 60 degrees is equal to opposite, it's Fg, and then divide by electrostatic force, and then tan 60 equal to Fg is the one that I'm looking for, and then the electrostatic force, it's 5.76 times 10 to the power negative 3. So in the calculator, if you say 1060, when you cross multiply, you have Fg equal to 1060 times 5.76 times 10 to the power negative 3. The answer here, it's 9.976 times 10 to the power negative 3. Was that newtons? That's the gravitational force. Now we have the gravitational force, and then the next thing, we go to the formula Fg is equal to mass times gravitational acceleration, and then we substitute 9.9766 times 10 to the power negative 3 equal to mass, the one that I want, times by 9.8, and then I divide by 9.8 both sides, 9.8, and then I'll have the mass, and then if I divide that by 9.8, so my mass is going to be 1.02 times 10 to the power negative 3 kilograms. That's the mass of the sphere R. We're looking for the mass of that. I hope that makes sense, guys. Cheers, bye.